Hi, welcome to this lesson on calculus, the second derivative. Let's have a look at question 2. So we're given a function f of x equals x plus 1 times x plus 3 times x minus 1. So if I were to expand this out, which we will see that the highest power ends up being a cube. So this is a cubic function. And again, the whole goal of this differential calculus is to be able to draw cubic functions to a very good accuracy. All right, so we've been looking at the first derivative. Now we have the second derivative, so we can get a better idea of what the shape of this function ends up looking like. So we're going to classify any stationary points, the intervals where the graph increases or decreases, and then classify any intervals of concavity and if there is an inflection point or not. Okay, so first of all, let's go ahead and expand this out. So I'm going to expand out the first two brackets and then expand it out with the last bracket. Okay, so let's expand that out. So what do we get? X squared, then we'll have a plus 3x and a plus 1x will give us a plus 4x. And then 3 times 1 is 3. Okay, and then that's all times x minus 1. Okay, and then let's expand that out. So I'll have x cubed minus x squared. So that's the first term multiplied out. Then I'll have plus 4x squared minus 4x. That's the second term expanded out. And then plus 3x minus 3. So let's group like terms. There's a single x cubed minus x squared plus 4x squared. That leaves you with positive 3x squared. Negative 4x plus 3x, that leaves you with negative x, and then minus 3. Okay, so that's a cubic function of the form ax cubed plus bx squared plus cx plus d. Okay, so now we can sort of get a rough sketch, right, from all the properties that we're going to look at. So let's get up a Cartesian plane. We can already tell what the x-intercepts are because this is nicely what we call in the factorized form. So if I plug in x equals negative 1, this whole thing becomes 0. So negative 1 is an x-intercept. Okay, what about at x equals negative 3? So if I plug in that as well, I'll also get 0. So that's a y-intercept. And then at x equals positive 1, that's also an x-intercept because it'll cut the graph there. Okay, but we don't know in what direction it's going in yet. So let's go ahead and find stationary points first. Okay, so stationary points. Set your first derivative equals to 0. Okay, let's use the power rule on this cubic function and then the sum and difference laws for derivatives. So that becomes 3x squared plus 6x minus 1 equals 0. Okay, so I'm going to go ahead and use the quadratic formula to find the values that satisfy that. So my little a here is 3, my b is 6, and my c is negative 1. So let's recall the quadratic formula. Negative b plus or minus square root of the discriminant term, which is b squared minus 4ac, and all of that gets divided by 2 times a. So that's equal to negative 6 plus or minus the square root of 6 squared minus 4 times 3 times negative 1. All over 2 times a is 2 times 3, which is 6. So let's find these two values on our calculator. So I'm going to go negative 6 plus first. Okay, 6 squared is 36 minus 4 times 3 times negative 1 all over 6. So I get x equals 0.15. I'm just going to go to 2 decimal places for now. Or x equals, what's the other value? So let's go ahead up here and do minus. So I get negative 2.15. Okay, so 0.15 is somewhere over here. Okay, we know there's going to be a turning point or a stationary point at that point. And then negative 2.5, it's somewhere over here. Okay, so that's negative 2.15, and that's 0.15. So we can find the values evaluated at the original function. So f of 0.15 and f of negative 2.15. So what I'm going to do is I'm going to keep those exact values in my calculator. So first I'm going to go delete and put plus. So that's that value. I'm going to go shift store A. I'm going to put that answer into A. Then I'm going to take the second answer and put it into my calculator as B. Okay, so the second answer was negative 6 minus the square root of 36 plus 12, if you expand that out, over 6. So that was the value, yeah. So shift store B. Okay, so now what I'm going to do is I'm going to take the original function, which is that. So I'm going to say open brackets, alpha A, or I can put it into this one rather. So alpha A cubed, this is the same function, plus 3 times alpha A squared minus alpha A minus 3. So that gives me negative 3.08. It's 2 decimal places. So this coordinate is 0.15, negative 3.08. Okay. And then similarly, I can change that and put it as a B. So let's change all those A's to B's. Alpha B, and then minus alpha B. And that gives you positive 3.08. Okay, so at negative 2.15, you get positive 3.08. Yeah. Okay, so let's go ahead and get a rough sketch of that. So negative 3.08 will be somewhere here, positive 3.08 will be somewhere up here. So that associates with that stationary point, and up here with that stationary point. So let's always label 0.15, negative 3.08, and then over here, negative 2.15, and positive 3.08. Okay, so we're drawing better and better accurate versions of this cubic function. Okay, what about intervals of increasing or decreasing? So let's go ahead and make some space here. So remember that this first derivative that we just did now, that tells us the critical values, which are the stationary points of the graph. So those critical values are what we're going to use now for the number line when we solve the first derivative greater than 0. So that'll be your interval of increasing. And then less than 0. That'll be your interval of decreasing. All right. So let's go ahead and do that. Okay. So I have for increasing, f prime x must be greater than 0, but that implies 3x squared plus 6x minus 1 must be greater than 0. So we've got our critical values. We found them. That's when it's equal to 0. So that's x is 0.15 or x equals negative 2.15. So on our number line, let's put that there. So negative 2.15 is here, and 0.15 is here somewhere. So all I need to do is test the regions. So I'm going to take a number bigger than 0.15. So I'm just going to take 1. If I plug that in, 1 squared is 1, times 3 is 3, plus 6, so that's 9, minus 1 is 8. So it's positive in that region, and open dots at your critical values because you're not including them. It's strictly greater than 0. Then if I take a value in between these values, so 0 is between these two numbers. So again, if I put 0 here, I'm going to end up with negative 1, so it's a negative sign. And if I put something very negative, like negative 3 here, that's going to be negative 3 is squared is 9, times 3 is 27, all right? Then you're going to have negative 3 times 6, 6, 12, 18, that's negative 18 minus 1. So if you do that calculation, you're still going to get a positive output. Okay, so increasing means that the positive intervals are what we are looking for. So x is an element from negative infinity all the way up to that negative 2.15, takes a break and then joins, so unions, with 0.15 all the way to positive infinity. Okay, then for intervals of decreasing, okay, for decreasing, that's f prime x less than 0. So again, we've already done all the hard work here, so we can see that the interval negative implies that x must be an element from negative 2.15 up to 0.15. Okay, so between these intervals, the graph is decreasing, okay, and in between these intervals here, the graph is increasing. So let's go ahead and draw a rough idea of what that looks like here. Okay, but we can actually get a much, much better accurate drawing of this by now looking at the second derivative for the concavity. Okay, so let's go ahead now and do the second derivative. All right, so I'm just gonna select some of these things over here and get rid of them. Okay, perfect. Okay, so let's recall we worked out the first derivative as 3x squared plus 6x minus 1. So now the second derivative is the derivative of that derivative function. So I apply the derivative once more, I get 6x plus 6. Okay, so for concave down, that must be the second derivative less than 0. So let's solve that. 6x plus 6 less than 0. So it's a linear inequality. We can solve for it. Bring the 6 across. I have 6x is less than negative 6. Then I can divide both sides by 6. And because 6 is positive, it doesn't change the sign. So x is less than negative 1. Or x is a real number. So in interval notation, that means x is an element from negative infinity to negative 1. The graph is concave down. So let's recall concave down has that bendy shape like that. And all the tangent lines are above the graph. Okay, what about concave up? So for the concave up interval, that's going to be when the second derivative is greater than 0. Okay, but then that just implies that 6x plus 6 is greater than 0. Take the 6 across as we did, we get 6x greater than negative 6. And if we divide both sides by positive 6, we get x is greater than negative 1. So on the interval x is an element from negative 1 to positive infinity, the graph has this bendy shape like that, concave up, because it's above its tangent lines. Okay. And then does this graph have a point of inflection? Well, we need to find the second derivative and set it equals to 0. So that implies 6x plus 6 equals 0. So take it across, I got 6x equals negative 6. Dividing both sides by 6, I get x equals negative 1. So at negative 1, which is the x-intercept actually, it changes concavity. Because we can see to the left of negative 1, it's concave down. And to the right of negative 1, it's concave up. Okay, so let's go ahead and draw those and put that together. Okay, so what I'm going to see here now is that less than negative 1, so less than this intercept, the graph must have a bendy shape that goes like that. Okay, then instead of the tangent lines lying above the graph now, the graph changes concavity at negative 1 and now bends that way. Okay, so we can see that the tangent lines to the left of negative 1 are lying above the graph, so the graph is down from the tangent lines, it's concave down there, and then this bendy shape after negative 1, all the tangent lines are below, so the graph is up from the tangent line, so it's concave up. Okay, so that is the entire process of looking at all the intervals of increasing, decreasing, where it's concave up, concave down, stationary points, and inflection points. Okay, the whole idea is to sketch cubic graphs to the highest degree of accuracy that we can, which we've seen here in this question, which is great. All right, I'll see you in the next one.